Statistics, in a way, is about probing the unknown. It's trying to go from uncertainty to something where you've got a level of numerical, or at least estimations of probabilities, or some feeling as to how likely something is to be true or not. But in the end, there is a big cloud of at the risk of citing a book title, A Cloud of Unknowing, but perhaps a little less spiritual than the original book title here. Now I want you to go back, and talked about this ages ago now, quite well, certainly previous videos. The job of statistics. The job of statistics was to take samples or data that you've collected from the real world, some sort of measurement of the real world, and then to turn that back and to be able to then say something about the world. So you've got something, you've got users, they're going to have some behaviour with your system. You do some sort of study and get data about them, and then you want to go back and say something with a level of belief that you're going to get it right about what they're actually like and how they're likely to behave in the future using your system or other systems. So it's this ability to turn back from measurement to actually looking at the real world that it was about. A key concept that you get in pretty much all kinds of statistics that you use, it's not just one kind, is the idea of conditional probability. And that sounds pretty scary. I mean, probability sounds a little scary. Conditional probability, wow. So you know to understand vaguely about probability. So if I toss a coin, 50% heads, 50% tails, probability. Conditional probability adds a little bit of knowledge, but it's not actually that much. So if I look outside my window, I might say, what's the probability that the road is busy, right? Well, how likely is it going to be busy? This is Tyree, so it's very low actually. But maybe I'm in a city, big main road. What's the probability the road's busy? It's probably busy a lot of the time. But say it's 4 a.m. on a Sunday morning. What's the probability that it's busy? And it's a different answer. So the probability given that it's 4 a.m., given the condition, given the context that it's 4 a.m. on a Sunday morning, changes our estimation of what that probability is. I was looking for, and I'm sorry, this is so small, I don't really have a big die. I must have one somewhere, but I couldn't find one. So a tiny little die here. It does have 6 sides, and it does have numbers on them all. So imagine I roll the die, and I've got it there, a bit like tossing a coin. I've done it anyway. I roll the die, and I can peek and see what it is. So what's the probability that if you roll the die, it's going to be a 6? Well, 1 in 6. Yep, you can do that one. Imagine I look and I say, it's 4 or bigger. Right, so I give you some information. Now, what's the probability that it's a 6, given the information I've given you? Well, now it's going to be 1 in 3, because it could be a 5, it could be a 4, it could be a 6. There's no reason why one of those should be any more likely than the others. So, given no knowledge, it's 1 in 6. But conditional on the knowledge that it's 4 or greater, then it suddenly becomes 1 in 3. Conditional probability is all about that idea that you're saying, what's the probability given I've got some knowledge? Right? Likelihood is another term, and likelihood really is just conditional probability. However, it's in the specific case of statistics, it's what's the probability that I'll get a measurement. So I've taken loads of people and I've got some measurements from them in terms of perhaps their response times to some sort of stimulus I've given them. I've popped up an advert, do they notice it and click through or something like that. So what's the probability of that measurement given some belief about the world? So say my belief about the world is that people's eyes are drawn to small kitty cats. Kittens, sorry, on the screen. So perhaps I put kittens on some of my adverts that pop up and I don't put them on others. And then I measure how likely they are. So what's the likelihood that I'll see certain response times given that belief about the world? So given something unknown about the world, of course I don't know, actually I probably have some idea about kitty cats and stuff, but say I don't know how likely people are to be affected by kittens. What I can do is say, if I believe that they are not affected at all, then I'd expect to see this result. If I believe they're expected, they have, say, 10% more likelihood to look at something if it's got a kitten on, then I'd expect this kind of response time. So likelihood is about that conditional probability of what measurements you're likely to get, given some belief about this uncertain world that we perhaps know little or perhaps nothing about. So if I've got my coin here and I toss, I haven't got my little board for putting them in, but anyway, if I've got my coin here and I toss it 6 times, the probability there'll be 6 heads is 1 in 64. That's 2, 4, 8, 16, 32, 60. I got my sums right. It's 1 in 64. Right? So if I toss it 6 times, the probability of getting 6 heads is 1 in 64 if it is a fair coin. So assuming it is a fair coin, the probability is 1 in 6. But is it fair? How do I know if it's fair? Actually, if I tossed it 1,000 times, they're all heads, I might start to doubt it. And statistics, again, is all about trying to quantify that doubt. So statistics turns it around. In one way, it's counterfactual. It says you can work out the likelihood of a measurement given it. So given this is fair, I can work out the likelihood of getting 6 heads. What statistics are trying to do is saying, well, okay, I don't know whether it's fair or not. But what I do know is I tossed the coin 6 times. I don't know whether people prefer system A or system B. What I do know is I asked 6 people and they all said they preferred system B. Do I think there's no difference between them, or do I think perhaps B might be just a tad better? Right? So what you do is you're taking measurement. You don't know about whether the coins are fair. A pretty good idea of whether the coin's fair actually, but when I do the electronic ones on screen, who knows, I might be fooling you and pretending they're fair. But given my users, are they going to be any different on the 2 systems? So we have uncertain knowledge about the real world. What we have is measurements. So what we want to do is take the likelihood of those measurements, given the uncertain knowledge, and turn it into uncertain statements about that uncertain knowledge of that unknown world, but based on the measurement. Sound good? And in various different ways. And different kinds of statistics try to do that twisting back in different ways. So going back to our picture, what we've got is the real world, but of course we've got lots of random effects. Our measurements have lots of randomness in. You know, the tossing of the coin, it could be either way. It doesn't end up as a half head, half tail. Sometimes it's a head, sometimes it's a tail. There's lots of randomness going in there, lots of things, lots of noise, lots of things we can't control, we can't measure. But we do have some idea of this likelihood, this probability of the likelihood of seeing some sort of measurements given something about the real world. And then what we're going to do is turn that back on itself and have some sort of uncertain conclusions about the real world, and they will always be uncertain. We won't have definitive answers. There'll always be a level of uncertainty, but we'll have reasonable levels of certainty about them, of the real world, based on the measurements we've got. We can do this in different kinds of ways, and you'll have come across these, and I'm sure at different stages. There's the most common technique used is what's called hypothesis testing. So when you've seen those dreaded p less than 0.5s and stuff like that, that's straightforward hypothesis testing. We'll talk more about this in a minute, but it's robust. It can be confusing what it actually means. As I said, because it's robust in various ways, it's used a lot. The other technique we'll talk about is confidence intervals, which is about putting bounds on things, saying, well, it's between here and here. Very powerful. In fact, I'm going to say later on that you should always do these. If you're going to do the first, you probably should do the second. But tend to be underused. And the reasons for that are interesting. I'm not quite sure why, but they are, and despite their power. both the traditional hypothesis testing and confidence intervals, or there's different kinds of confidence intervals, but the most common kind, use the same underlying methods and theories and assumptions. So they're in one way very similar in terms of the way they approach the world. It's just presenting the outputs in different ways. Bayesian statistics, different kettle of fish, has completely different approaches, mathematically really clean. So people who like things that look nice and tidy will love Bayesian statistics, but tend to be a little fragile if the assumptions break down a bit. They also have various issues. I've mentioned independence. There's a number of different issues. There's some dangers. They're dangerous, not things have to happen, of confirmation bias, but we'll see these emerge later. The most common way these are dealt with is where you have, we talked about that likelihood, where you know what that conditional is. You've got some idea. That might be based on the kind of things. So coin tossing, you've got a very good model of what happens, and you get lots of coin tosses one after another. Sometimes you don't, and there are other methods, and particular simulation methods, which can be used where you don't have that strong likelihood function in the start. That can be used with traditional hypothesis testing, with confidence intervals, and with Bayesian stats. So it's more of an orthogonal thing, is how you get that likelihood knowledge in the first place. The examples we'll give, they're all, should we say, one's a sort of theoretical or model where you know for some reason what it is. But simulation methods are one of the ways you can sort of bootstrap yourself if you don't even have that knowledge. And we'll see examples of all of these and discuss them in some depth in the following videos.